Greetings, Earthlings. Welcome back to the Art of Math. Today we're going to go over a cool solution and an extension to the same farming problem from the previous video. So, a quick recap. In the original, we had this x by y rectangle, and we were given a constraint for the perimeter. So the sum of all of these is 2x and 2y, and we said that's equal to 20. So if we divide by 2, we got that x plus y is 10, and then the area is x times y. So if we plug this one in by rearranging into here for y, we would get x times 10 minus x with these two. All right, and then from here we said that we could use the properties of the vertex or axis of symmetry to find the best value of x to maximize the area of this plot of land. That's well and all, that's very nice. However, I want to show you perhaps a more intuitive or alternate or a cool solution to do the same problem. Rather than refer to this as x by y, let's refer to these as x minus something and then x plus that same something. That may seem a little mysterious, so to understand where this comes from, let's look at some practical numbers. Since we know that x plus y have to sum to 10 from the original, we could try 1 by 9 and see the area sucks. The area is 9, that's really small. We could try 2 by 8, a little better, 16, and keep going higher and higher till we equalize them, and they're 5 and 5, and finally we get 25. And by symmetry, if we try to go past this 6 by 4, we're just going to start to decrease again. So this gives us the idea that all of these can be thought of as 5 minus a number and 5 plus a number. Again, which one is your width and length doesn't matter, so don't get hung up on that. So for example, if we wanted to do the 1 by 9, the 1 can be thought of as a 5 minus 4, and the 9 can be thought of as a 5 plus 4. So in the general case, we can find this area by multiplying, and we get x plus a times x minus a, and that's x squared minus a squared. All the ax, negative ax stuff cancels. So let's go to our specific example where we have 5 minus a, not x, but 5 now, 5 minus a and 5 plus a. So using the same algebraic expansion, we have the area is 5 plus a, the width, times the length, and then this multiplied gets us 25 minus a squared. So what's cool about this? This tells us that this 25 is not changing, that's a number. However, we are free to change this a. So since we want the maximum area, we don't want to subtract anything, right? Because a squared number is going to be non-negative. So this is either 0 or larger, and if we set a, let's say, to 1, then we're subtracting 1. We don't want to do that. So let's set a to 0, and we get 25 minus 0, so the maximum area is 25, corresponding to 5 minus 0, 5 plus 0. So basically we have a square. So I think that's maybe a more intuitive way by just playing around with it and seeing that, hey, we want to equalize the dimensions due to this simple expansion and square property over here. So rather than going all the way to quadratic equations and vertices, but that's also a way to do it. All right, so that's one point I wanted to mention, and I want to leave you guys with this. Here's an extension. In these cases, we've been considering rectangles. Now, what's the maximum area? Same problem, and what's the corresponding shape? If I told you that we're not limited to rectangles, so you can have a triangle, a pentagon, whatever shape you want. The only constraint is the perimeter, again, has to be 20, just like in the original. So you may think you have an answer, and my challenge to you in that case is why? See if you could prove it or argue why your answer is the best answer. Okay, I'll see you guys in the next video.